Hey guys, we are going to talk about the very last section of this energy unit, and it's on entropy. So, entropy is just a measure of disorder. So, I'm sure that all of you are familiar with disorder because maybe you have a really nice, clean room, you've maybe spring cleaned everything, but you'll notice that you initially start off with everything really nice and neat. And all of a sudden, as time goes on, you notice that it doesn't get quite as clean. Dust collects, clothes are on the floor. So you tend towards more disorder. Or the same thing with your locker or your car. You can start out with everything nice and neat, but as time goes on, it tends to become more disordered. Okay, so entropy is a natural process and it's just a measurement of the disorder in the universe. So it's recognized as an S. So delta S is the symbol for it because E was already taken for enthalpy, or I'm sorry, for energy. So when E was already taken for energy, they're going to go to S for entropy. So you'll see that if you have a positive S, it means your entropy is increasing. It's becoming more and more disordered. Whereas a negative delta S means your entropy is decreasing. It's actually creating more order. Okay. So spontaneous reactions are reactions that occur without any outside intervention. So if you think about this in terms of when you've ever reacted baking soda and vinegar, the reaction just happens. Okay. So spontaneity of a reaction is going to depend on a couple different things. It's going to depend on both the enthalpy. So we talked about that before, which is your heat energy, and the entropy, which is the measurement of the disorder, the actual changes with entropy. And there's two natural processes that you see in the universe. It's very natural to get lower in energy, and it's natural to get higher in entropy. So it's going to become lower, giving up energy, and then it's just become more and more disordered. So again, you think about your room, it's going to become more and more disordered as time goes on. Okay, there's a couple different ways that you can look at entropy. So what you're going to look at, one of the things is solid versus liquid versus gas. Okay, when you're looking at the order of something, the state of matter really plays a part. So if you think about a gas and how gases are, your molecules are kind of constant random motion. They're bouncing off each other, they're bouncing off the walls or whatever container they're in. But there's really no rhyme or reason to the direction until they hit and they go the opposite direction. So essentially, in a gas, it's the highest amount of entropy in all of your states of matter because it's the most chaotic. Okay, there's not a whole lot of order as far as your gas molecules go. Okay, liquids, little bit more. Okay, order. It flows, so those molecules are still moving, but you're going to see a little bit more order. So the entropy is going to be a little bit less. And then solids by far are going to have the lowest entropy, so the most order. Okay, because as you go from a solid to a liquid, it gets a little bit more disordered. From a liquid to a gas, it becomes even more disordered. So depending on the phase and the state of matter you're in, it's going to really kind of dictate the entropy for that molecule. So we're going to, in a second, look at all of the ways that you can decide whether it's increasing or decreasing. And the state of matter is one of the first ones you want to look at, simply because as you increase from solid liquid to a gas, you're increasing the disorder. So you're increasing the entropy. So we are going to look at different ways that you can decide whether it's increasing or decreasing. So state of matter, absolutely number one. Look at is it changing? Is it going from a solid or liquid to a gas? So for example, I have this little equation right here. I have my B molecule, which is a liquid, and it's going to change into a gas on the product side. So this would be an increase in entropy. I have some order, and it's going to more disorder. So liquids are going to have a lower amount of entropy, gases higher. So when you see a change in state like this is going to be an example of increasing entropy. If you were to say go the other direction, let's just say we had a liquid that we were going to freeze into a solid, that would be a decrease in entropy. You would actually see more order form when it goes from a liquid, which is a little bit more of a chaotic state, than a solid is. So if you have a change in state, that's one of the first things you need to look for. That's one of the most important things. Okay, but let's just say that you have an equation where everything is in the same state. There's no change of state. The next thing you would want to look for is change in the number of molecules. So for example, if you have maybe one molecule that's being broken down into multiple molecules, maybe you have more moles on one side than the other. Those are things that you want to pay attention to, because generally speaking, the more molecules you have, the more chaos you have, or the chance of chaos that you have. So if all of your changes of state, there's no change, they're all in the same phase, then you're going to look at a change in the number of molecules, okay? But now let's just say that there were two reactants and they formed two products. So there really wasn't a change in the number of molecules. Something else that you can look at is complexity. And complexity is how many of each atom is actually bonded together. So that would be another example that you could look at as far as determining if it's increasing or decreasing. So the more atoms there are in a molecule, the more disorder there is. Okay? If you have all of those things and nothing's really helping either way, you can look at the dissolution process. Dissolution process is just how to dissolve. So if you think about when you took salt and you put it in water and you stir, you're actually taking that solid salt crystal and you're dissolving it into its individual ions. So you're taking a solid and you're kind of putting it into that aqueous form. It's actually going from a solid to multiple pieces in its individual ion form. So generally, when you dissolve something, you are creating more disorder. So again, more disorder means higher entropy. Okay, and then another thing is an increase in the volume of a gas. Okay, so the more there is, again, the higher the chance of disorder, the higher the entropy. So I have at the bottom of this a little equation here. So this is dissolving salt, like I just talked about, salt and water, solid and liquid, and it's going to go into individual ions. It's being broken apart. So here it was one nice ionic crystal. It dissolves in water. Now you have your individual ions. So my entropy is increasing. I'm creating more disorder. So this would be a positive entropy. Whereas this example, I have two reactants that are forming one product. All of them are in the gas phase, okay? But if you look at the number of molecules here, I have two on the left-hand side for my reactants, and they're forming one total product. So I'm actually, by going from multiples into one, I'm actually creating more order. So I'm less disordered. So this is going to be a negative entropy because entropy is decreasing. I'm creating more order when I go from multiples into one. Okay, so we're going to look at a couple examples of how entropy may increase or decrease. Okay, so if you look at this first example, you have a liquid and then you have a gas. So I have water in both sides here, but this is a liquid, this is a gas. So this is going to be a change of state. Entropy is going to increase because my liquid phase versus my gas phase has a higher disorder. Okay, there's going to be a higher disorder. So this is an increase in my entropy. So that one's an increase there, okay, because it went from a liquid to a gas. Okay, B, I've got sucrose, okay, which is just solid sugar, and I've got water, and this is an example of a dissolution. So if you'll notice that sucrose was in that solid stage, and it dissolved in water, and now it's in that aqueous form. It's still sucrose on both sides. I didn't break up sucrose other than all of these as the solid crystal. You had a ton of sucrose molecules together, whereas once they dissolved in water, now you have individual sucrose molecules that are going to be in your solution. So this is also an increase in entropy because you have, that's much better, because you have a solution that's being formed. You have a dissolving of solid in the liquid, and it's creating individual sucrose molecules to be in that solution. Okay, here I have glucose versus sucrose. So both are formed of carbon, hydrogen, and oxygen. So this would be an example of complexity. So here I have 6 carbon, 12 hydrogen, 6 oxygen, whereas over here I have 12 carbon, 22 hydrogen, and 11 oxygen. So this is going to be my example of higher entropy simply because it's a more complex molecule. Again, the more atoms you have, the more chaos you have. So that's going to be an example of entropy increasing because of the complexity. Here, again, I have water, but water at 55 degrees versus water at 25 degrees. I mentioned before, temperature has an effect on those molecules. And the higher the temp, the higher the entropy because those molecules are moving faster. So water at 55 degrees has a higher entropy than water at 25 degrees because of the movement of those molecules. Anytime you increase temp, you're going to increase that entropy. Okay, and then letter E, you have potassium chlorate that's being broken down into a solid and a gas. So you have one that's being broken down into many. One of those phases is going to be gas forms. So your product side is going to have a higher entropy than your reactant side did because you only had one over here, it was in its solid form. Again, solid being the least amount of entropy. Versus on here, I was broken down into multiple molecules and compounds, and I have one that's in solid and one that's in gas form. So based on that, the products are going to have a higher entropy than my reactants did. All right, this one's the last one on this page. I have gas, gas, gas. So all of my phases are the same, so there's no change in state there. So again, look at the number of molecules you had. Here I have SF4 and I have fluorine gas. They're combining to form 1 mole of sulfur hexafluoride. So again, because you have multiples combining into one, you're actually creating less disorder. So on this case, my delta S, my entropy is actually negative because I'm creating more order by combining it into one molecule. Okay, so again, just keep in mind that higher the entropy, the more disorder, the lower entropy, your negative is more ordered. So it just kind of depends on all of those things that we had previously just talked about. Okay, so the second law of thermodynamics is entropy is always increasing. So you can calculate entropy changes. Similar, we did this when we talked about enthalpy, but just like you saw with enthalpy, you have an equation that you can plug your values into. So you can do the same thing with entropy. So you have, again, your entropy, your final entropies minus your initial entropies, and these are based off of a chart. So you have a chart of S values, just like you had a chart of enthalpy values of your height or your heat values, okay? And so they're all calculated amounts. So entropy values that you'll see on this chart are all based on a reference point of 0 entropy. So if you can think about this for a second, in a perfect crystalline solid, okay, at 0 Kelvin, so absolute 0, technically there should be 0 entropy because you can't really measure disorder. Okay, that's a hard thing to actually measure. So Linus Pauling came up with this, that if we think of a perfect crystalline solid at 0 Kelvin, absolute 0, it would have absolutely 0 entropy. So all of these values on this chart are based off of that reference point, okay? So all of these that you see on this chart are going to be the values for 1 mole of whatever substance you're looking at. Okay, so you see this little S means standard molar entropy. Okay, so for 1 mole, it'll be that calculated amount, and standard state's just at 1 atm. So this equation is very similar to what you saw again for enthalpy. You have your delta change in entropy is going to be based off of the sum of your entropy products minus the sum of your entropy reactants. So you're going to look at your entropy values based off of a chart, products, you're going to add up your products, and then you're going to subtract out whatever the sum of your reactants are. So similar equation, except now instead of your delta H, like we did with enthalpy, you're looking at your delta S, which is entropy, okay? But it's still the same idea with products minus reactants. Same thing that you did with enthalpy. You also want to make sure that you multiply the values from your balanced equation. So I'm going to take the number of moles of my balanced equation and multiply it times its value. Because if you don't, then you're going to, again, end up with a wrong answer, which is not what we want here. So the other thing that I want to also mention is that my entropy units, are in joules per Kelvin, and sometimes you'll see dot mole, okay, joules per Kelvin mole. Whereas my heat, my enthalpy, my delta H units were actually in kilojoules. Okay, so if you see ever these in the same equation, those are things that you would want to pay attention to because one's in joules and one's in kilojoules. So if you had to use those kind of back and forth, you would have to make sure that you choose joules or kilojoules and convert. So just kind of that's worth mentioning as far as the units go. So let's show an example of what a problem would look like. So I'm going to calculate the entropy for the following reaction. So notice I have 2 moles of water in liquid form, and it's being broken down into 2 moles of hydrogen gas and 1 mole of oxygen gas. So I'm going to take my value chart. I'm going to look up my S values. And water in liquid form, the value is 70 joules per Kelvin mole. And then I'm going to multiply that by 2 because I have 2 moles of that. H2 is going to have a value of 130.7 joules per Kelvin mole. I have 2 moles of that, so I'm going to make sure that I multiply that by 2. And then oxygen is going to have a value of 205 joules per Kelvin mole. And notice this is a little bit different than enthalpy because in enthalpy, your H, if they were in their naturally occurring form, those values were 0. So in enthalpy, when we looked at that video, hydrogen and oxygen would be a value of 0. However, unlike enthalpy, entropy is a measure of disorder, and everything has some level of disorder. Okay, some higher than others and some lower than others, but everything has some kind of disorder. So you will not see any 0 values for your entropy on these charts because everything has some kind of measure of disorder. Okay, and if you look, this one is 70 and that's in liquid form. This one's 130, this one's 205, and both of those are in gas form. So right there, you can even see that state because liquid is a little bit lower in entropy, that value's lower. Gases have a higher entropy, and you'll notice that those values are higher than that liquid was. So just something to note. Okay, so you're going to take these values, products minus reactants, just like we did before. So I'm going to take my 2 times 130.7, and I'm going to add that to 205. There's my product side. When I do that, I get 466.4. And then if I multiply 2 times 70, I get 140. And I'm going to subtract those. I get 326.4. So my delta S is positive. Again, it's positive, so it's more disorder, okay, which makes sense because I'm going from a liquid to a gas. So I am creating more disorder because those phases are going from somewhat ordered to not ordered at all. So that makes sense that my entropy is increasing here, okay? So again, you won't be able to do that without these values. So you would have to have those values in order to plug this stuff in, okay? All right. So just to kind of wrap up everything, 2 natural trends that I really want you to keep in mind is that for nature, the universe in general, it is natural for things to get lower in energy and to become higher in entropy. So low in energy, more disordered. So again, always think about your room or your locker or your car, whatever you live in the most, okay? It's going to have a tendency to get more disordered. Okay, this is also why exothermic reactions are more common. You see a lot of negative delta H's because of the exothermic reactions and things get more disordered, so positive delta S's. So exothermic, increase in entropy, those are natural to be that way. So lower in energy, higher in entropy, natural, that's just how the universe tends towards. Okay, and then there's a little cartoon I have here. It says, Mom, you can't fight the second law of thermodynamics. All things, which includes bedrooms, move from a state of order to disorder. So here he's using science to explain why his room is a mess. So maybe next time your room is a mess or your car is a mess and your mom or dad tells you to clean it, you can say, hey, listen, this is just the second law of thermodynamics. Okay. All right, guys, thanks for listening, and hopefully you feel better about entropy.